Welcome back to the deep dive. If you are listening to this, you are probably someone who appreciates that in technology, as in life, you often can't have it all. Today, we are strapping in for a high-altitude flight right into the core dilemmas of system architecture, the hard, immutable laws of computing that force engineers to choose between things they absolutely want. Our mission today is to dive deep into the fundamental limits of system design. We're talking about the unavoidable trade-offs that dictate how massive complex systems, especially those handling your most sensitive health or financial data, can actually be built. If you've ever wondered why your system is super fast but sometimes serves stale data, or why your privacy controls suddenly slow down your application, we're going to give you the blueprint of that necessary compromise.
And this is more than just a theoretical exercise. Understanding these limitations is really the key to building resilient and effective technology. We are not searching for some mythical perfect system where every requirement is maxed out. We are hunting for the optimal compromise that achieves, good enough functionality within real-world constraints. We'll start with the godfather of all distributed systems limitations, the CAP Theorem, and then expand that foundational model to tackle the intense modern hurdles, most notably the complex trade-off between privacy, performance, and cost, or PPC.
That sets our agenda perfectly. Our mission is to unpack foundational distributed systems limits, that's CAP, and then explore the complex, multidimensional, modern system hurdle, the privacy performance cost trade-off. We'll be examining some really cutting-edge solutions designed specifically to cope with these inherent constraints. So, let's get started with part one. The non-negotiable laws of distributed computing. The CAP theorem, sometimes known as Brewer's theorem, is where every conversation about distributed systems architecture really has to begin. It provides the fundamental constraint for distributed databases and services. It dictates the ultimate limits of what a system operating across a network can achieve. It really forces a choice.
That phrase, choose two, is the simplest summary. But we have to define those three elements with some precision, because the consequences of choosing incorrectly are, well, they can be catastrophic for a large application. So C stands for consistency. In a distributed system, consistency guarantees that every read receives the most recent write that occurred in the system. Imagine you update your bank balance on one server. If you immediately check that balance via a different server in the network, consistency demands that you see that freshly written data. If the system can't guarantee that, it has to return an error. So consistency, at its heart, it guarantees data integrity across the distributed network at any moment in time. Then A stands for availability. Availability is the guarantee that every request made to the system receives a non-error response. It guarantees uptime, responsiveness. Critically, though, availability does not guarantee that the response contains the most recent write. It just guarantees that the system is functional and ready to serve requests.
So it'll give you something, just not necessarily the very latest something.
Exactly. Think of a social media feed. You want to see a post immediately, even if it's a few seconds old. And finally, P stands for partition tolerance. A network partition is a failure scenario where the network loses communication between two or more nodes. Partition tolerance means the system must continue to operate and function reliably, despite these arbitrary message losses or node failures. It's the ability to withstand the messy reality of network infrastructure.
And here's where the constraint really kicks in, the core of the theorem. The theorem states that during a network partition, when that P is in effect, you must sacrifice either consistency, C, or availability, A. You cannot maintain all three simultaneously when the network is broken. So we immediately see two primary camps in system design. You have the CP systems, which prioritize consistency over availability. In the event of a network split, if they can't guarantee that the data they're about to serve is fresh and accurate, they'll just refuse the request entirely. They'll return an error. They choose data integrity as the non-negotiable attribute, prioritizing correctness over uptime during a failure.
And then you have the AP systems, which do the opposite. They prioritize availability over consistency. During a partition, they continue accepting reads and writes, making sure every user request gets an immediate response. They sacrifice that immediate synchronization, risking serving stale or slightly out-of-sync data. This is the whole world of eventually consistent systems, a concept brilliantly framed by Werner Vogels, the CTO of Amazon.
So the data will sync up eventually once the network is fixed, but for a short time, you're trading accuracy for just being online.
Precisely.
What's fascinating here is how the real world turns this theoretical choice into a practical certainty. I mean, why can't we just choose to be a CA system, just guarantee both consistency and availability?
Because partition tolerance, the P, it's not optional in any large, modern, globally scaled environment. It's just not. If your system operates across multiple racks in a data center or across continents, networks will fail. Routers glitch, fibers get cut, latency spikes.
Things happen.
Things happen. If your system couldn't tolerate partitions, it would just break down every time there was a flicker making the whole system architecturally unsound for any kind of scale. This means that for any real-world large-scale system, P is a given. It's a fact of life. So the only operational choice you actually have is between C or A. Think about it in terms of product requirements. If you are building a financial ledger where every single penny must be accounted for before a transaction is committed, you absolutely must be a CP system.
You'd rather have an error message than a wrong balance.
Exactly. You'd rather return an error than double spend. But if you're building a recommendation engine, you prioritize the user seeing any result instantly. That's availability, even if that recommendation is based on a profile that's 30 seconds old. The stakes determine the compromise.
It's the ultimate reality check. You cannot scale indefinitely and guarantee transactional integrity instantaneously, all while guaranteeing 100% uptime. The physics of distributed networks just won't allow it.
Okay, so CAPT sets the foundational rule for data management, but this whole philosophy of unavoidable trade-offs bleeds into every other aspect of engineering. Let's move beyond the database layer and look at the general constraints system designers face every day. And let's start with the duo that often causes the most confusion: scalability versus performance. They're related, but they're not the same thing at all.
Not at all. Scalability is the system's ability to handle increasing demands, more users, more data, more operations in a graceful way. It's asking the question, can the system grow and handle 10 times its current load without melting down? It's all about handling volume and size. Performance, on the other hand, is about speed and responsiveness. It focuses on time metrics. How quickly does the system respond to a single user's click? How much CPU power is required for one specific task? And the tension here is just inherent. To achieve massive scalability, you must distribute your workload. You have to. You break the system into smaller pieces, spread them across many machines. But that act of distribution, it introduces communication overhead. Nodes have to synchronize, they have to send requests across the network, coordinate transactions. Every network hop, every lock, every little sync step is a tiny bit of time and processing power that hurts the individual performance metric. You might create a massive horizontally scaled platform that can handle 1 billion users, but the complexity of coordinating all of that might add just enough overhead to slow down the experience for any single user by, say, a critical 100 milliseconds.
It's that classic inverse relationship. And this leads us directly to the architectural choice between vertical scaling versus horizontal scaling, which is really a choice between simplicity and resilience. Vertical scaling, or scaling up, is simple. You take one server and you just add more resources. A faster CPU, more RAM, bigger disks. The advantage is that there's very low architectural overhead. The system stays conceptually simple, but its drawback is that it's constrained by the physical limits of hardware and, more importantly,
It creates a single point of failure.
a huge one. If that one super machine goes down, your entire service just vanishes.
So horizontal scaling, or scaling out, is the mandatory approach for massive scale. You just add more machines to distribute the load. This avoids that single point of failure problem. It ensures resilience and theoretically offers infinite scaling potential. But like you said, this is where the complexity budget starts running high. Now you need sophisticated load balancers, service discovery, robust data synchronization, all of that stuff.
Right. It's a trade-off where you're buying resilience and capacity, but you're paying for it with architectural simplicity and a lot more operational overhead.
So if architectural complexity is one constraint, operational responsiveness is another. Let's look at the critical trade-off between latency versus throughput.
So latency measures time. Specifically, it's the time delay between you requesting an operation and receiving the first response, the speed of a single action. Low latency is crucial for anything involving user interaction, like clicking a purchase button, or for high-frequency trading platforms where milliseconds literally equal millions of dollars. Throughput, on the other hand, measures volume. It's the amount of work processed over a given period, the rate at which the system can handle concurrent workloads. For instance, a system might have very low latency, responding quickly to single requests, but very low throughput, meaning it could only handle a handful of users at the same time.
And the tension comes from how you prioritize resources. If you engineer your system for ultra-low latency, you often dedicate maximum resources immediately to that one task. You might skip things like batch processing or complex queuing. This ensures a quick response for that individual user, but it might leave other resources idling or prevent the system from efficiently handling a massive simultaneous influx of work. And that limits total throughput. Conversely, systems that are engineered for high throughput often use batching, queuing, and serialization to maximize CPU use, making sure they process the maximum volume of requests possible. But that strategy often involves slightly longer queue times or processing delays for any individual request, which means higher latency for the single user, even if the overall system is highly productive.
You always have to make that compromise. Quick individual responses versus maximum work volume processed. And we see this dichotomy play out in fundamental data processing choices all the time. Batch processing versus stream processing. Batch processing is all about efficiency and scale over time. You collect and aggregate data over a fixed period, say 24 hours of sensor data, and then you execute all the processing at once. This approach optimizes resource use by processing data in bulk, and it's perfect for tasks that can tolerate delayed results, like generating daily reports or processing monthly utility bills.
And it's cost efficient, right? Because you only spin up the heavy computation when the batch actually runs. Stream processing is the total opposite. It deals with continuous data flow in real time, processing data almost immediately as it arrives. It's essential for time-sensitive applications like real-time fraud detection, patient monitoring in healthcare, or watching a livestock ticker. While stream processing offers low latency and immediate insight, it requires immediate resource allocation and constant system readiness, which translates directly to higher operational costs and more complex infrastructure.
It's that unavoidable trade-off again, delayed results and lower cost, or immediate results and higher operational complexity and cost. And if CAP provided the foundational constraints for infrastructure, then the Privacy Performance Cost Triangle, or PPC, defines the constraints around handling sensitive data. This is the critical modern system hurdle, especially in fields like smart healthcare, machine learning, and the Internet of Things. These systems require continuous collection and analysis of highly sensitive user data, your location, biometric markers, financial transactions, to provide personalized services.
So the complexity has just exponentially increased. We've moved from a simple binary constraint, C or A, to a truly multi-dimensional optimization challenge. Let's really solidify the three corners of this impossibility triangle. First, privacy. This is the goal of protecting sensitive user data. This includes adhering to modern regulations like GDPR or HIPAA and ensuring the data is protected from threats like identity linkage, profiling, or tracking. We're talking about preventing the leakage of protected health information or personally identifiable information.
Second, performance utility. This covers how well the system actually works in terms of speed, accuracy, and just overall usefulness. If you apply privacy preservation techniques, but they make your machine learning model's predictions totally useless, or if they add seconds of latency to a real-time operation, you failed the performance test. The system has to remain useful. And third, cost resources. C. This is the operational overhead. When we talk about cloud data centers, cost is financial, how much you pay for CPU time. But when we talk about IoT and edge computing, cost is also device resource consumption, the amount of memory, CPU cycles, and network bandwidth an operation uses.
Which is a huge constraint when you're dealing with these cheap, resource-limited edge devices like simple sensors.
A massive constraint.
And the core conflict is that traditional superficial privacy techniques like just stripping names off a database record, pseudonymization, they are completely insufficient for today's big data challenges. Modern data is so voluminous and diverse that linkage attacks can easily re-identify people even from so-called anonymized datasets.
Which means engineers must resort to more sophisticated methods like generalization, suppression, or heavy cryptography. And these modern techniques, they introduce significant, non-trivial overheads that invariably harm performance and rapidly increase resource use, driving us straight into this trilemma.
We have some specific data that really lays bare the severity of this cost, especially on those resource-constrained devices. Let's look at a scenario with an engineer trying to ensure privacy for data processed on a basic edge device, like a Raspberry Pi Model A, which has very limited RAM and processing power.
Right. The sources show the catastrophic effect of simply trying to make all data features private using generalization techniques. For a representative dataset from Fitbit logs, the memory footprint for processing the raw, non-private data was about 247 KB. It's tiny, but when the system tried to apply privacy functions to all the features, the memory required for the data, the privacy code, and the associated data structures, it just skyrocketed.
Yeah.
The total memory consumption jumped to 2,283 kBD. That is nearly a tenfold increase in memory usage. For a device with maybe only 512 megabytes of shared RAM, this kind of increase is catastrophic. It'd easily lead to memory exhaustion.
So it's using up to twice the overall resources compared to the non-private version just to stay running.
At least. It's a huge hit.
And what if you switch from that kind of generalization to stronger cryptographic techniques? The performance hit must become immediately apparent as latency.
Oh, absolutely. Full cryptographic solutions, which offer the strongest security guarantees, can introduce processing times of 2 to 5 seconds per operation. If your IoT device is supposed to be continuously monitoring a piece of machinery or a patient's heart rate and alerting in milliseconds, adding seconds of latency is a death sentence for the application's utility.
So you're trading instantaneous reaction time for maximum privacy, a trade-off that's just unacceptable in real-time environments. So we can't simultaneously achieve strong privacy, high performance, A&D, low cost. This forces us to confront the central engineering question of this deep dive. If we must compromise, how do we strategically select what to compromise to get the best outcome, especially when resources are scarce and, ethically and legally, user privacy is non-negotiable?
This is where static architecture fails and intelligent dynamic design has to take over. The solution is not to just brute force maximum privacy everywhere. It's to employ reconfigurable privacy, the concept of dynamically selecting which features to protect based on the current context, the device's resource availability, and the specific threat model.
And that brings us to the dynamic iterative greedy search, or DIG's algorithm. This sounds like a sophisticated mechanism for triage, for managing resources by partitioning data.
That's exactly what it is. DIGS is designed to navigate that PPC triangle dynamically on resource-limited hardware. Its first critical step is classification. It partitions the data features into two groups based on threat severity. First, you have essential features, ESIF. These are features that must be private no matter what, regardless of the resource crunch. Think biographical information like age, gender, height, and weight in a health data set. These are the core identifiers, the non-negotiables. Then you have non-essential features, EAF. These pose a lower individual risk, or they contribute less uniquely to identification. They're the features whose privacy can be negotiated or even compromised if you hit a resource limit.
So the essential features are always private, consuming a base level of resources, and the non-essential features are the variable elements that DIGs intelligently selects from.
Yes. The mechanism involves applying what are called injective privacy functions. These are techniques like generalization, where you map a specific value, like a bank balance, to a range of values, like a $500 range. Or suppression, where you just remove the feature entirely. DIGS iteratively searches through combinations of the NEF, applying these functions, and at the same time it calculates the precise resource consumption for each combination. Memory overhead, required network bandwidth, and the number of processor instructions. It's quantifying the cost of privacy per feature set.
Let's look at the payoff using that Fitbit dataset example again. The system starts with 4 mandatory essential features being kept private. The rest of the data has 13 non-essential features, which leads to over 700 possible combinations of privacy settings. If an engineer tried to manually determine the best balance, it would just be guesswork.
DIGS removes the guesswork. It identified an optimal set of 9 additional NEF that could be made private, using generalization techniques without exceeding the predefined resource cap of that Raspberry Pi. This automated strategic compromise translated into really tangible efficiency gains compared to the naive approach of just trying to make all 13 NEF private. Specifically, this optimized selection saved 26.21% of memory, 30.5% of network bandwidth, and 16.67% of CPU instructions.
And in the context of millions of low-power IoT devices, those percentage savings translate to massive operational cost reductions and dramatically extended battery life.
Huge savings at scale.
This is the practical engineering breakthrough, but the major aha moment, which you alluded to earlier, is completely counterintuitive. DIGS optimizes for resource savings and privacy, but the performance, the utility of the data for the machine learning model actually improved. How is it possible that making data less accurate by generalizing it resulted in better model performance?
That is the core insight into data preparation for machine learning. We saw the system training an SVM classification model to predict user health status. The non-private baseline model achieved 96.41% accuracy. But the model trained on the data that went through the DIGS optimization, with 13 features strategically generalized, it achieved 96.79% accuracy. It's a slight but meaningful increase. This happened because the generalization process forces continuous, sometimes noisy numerical data into discrete categorical buckets.
Like a specific temperature becomes a temperature range.
Exactly. The system then uses one hot encoding on these new categorical features. Support vector machines, SVMs, are sensitive to feature scaling and dimensionality. They often perform better when they're provided with clean, well-defined categorical inputs rather than noisy, high-precision continuous variables.
So by imposing privacy constraints, we inadvertently simplify the learning problem for the SVM.
That's it. This proves that optimizing for privacy can actually be a form of data preparation that enhances utility. It's fascinating. #B, quantifiable privacy, differential privacy DP.
That example shows us how to intelligently manage resources and utility, but let's address the holy grail, provable privacy. We need techniques that let us share sensitive data analytics without risk. And that brings us to differential privacy, DP.
DP is the solution for mathematically provable privacy guarantees. It allows organizations to compute and share statistical analysis like finding the average patient age in a group while guaranteeing a quantifiable limit on the privacy loss that occurred. This loss is measured by the privacy loss budget, which is symbolized as epsilon or epsilon. The mechanism is really elegant. DP achieves privacy by adding controlled, calibrated noise. This noise, typically from a Laplacian or Gaussian distribution, is added to the data, or more commonly, to the query results, and the amount of noise is directly proportional to the statistical sensitivity of the function you're querying.
Okay, statistical sensitivity. Let's be clear on that. What exactly does that measure?
So 6C measures the maximum amount that the output of a function could change if you removed or added just one person's data. If you're calculating the average age of 1 million patients, removing one patient won't change the average much. The sensitivity is low.
Right.
But if you were calculating the maximum salary, removing one entry might change the result a lot. The sensitivity is high. The DP mechanism uses this measure to ensure that the noise it adds completely masks the contribution of any single individual in the dataset.
So the trade-off is built directly into that epsilon value. Lower epsilon means higher privacy because more noise is added, making it harder to re-identify someone. But that high noise level simultaneously results in lower output accuracy or utility. And we see this principle applied perfectly in medical contexts with tools like PyDeepLeap. This is a specialized Python differential privacy library designed for private medical data analytics, allowing hospitals to share aggregate cohort data without exposing sensitive patient information.
Right. PyDeepLeap is designed to handle standard statistical queries like count, average, median, variance. To help the user navigate the epsilon trade-off, it uses a binary search algorithm to automatically select the right epsilon value based on a user-defined noise factor, usually set to low, medium, or high.
So it takes the burden off the analyst from having to calculate epsilon manually.
It does. For queries like calculating the average patient age versus their PIRS scores, which is great for prostate cancer risk, the library applies the Laplacian mechanism. The result is a visualization where the general trends are perfectly preserved. You can see the average age for higher scores is in the 60s and 70s. But the calibrated noise ensures that if someone tried to figure out if a specific 45-year-old patient was in that data set, the noise would mathematically prevent that inference. It fulfills the secrecy requirement without sacrificing that aggregate utility.
DP sounds incredibly powerful for aggregate analysis, but is there a limit to the utility loss organizations can tolerate? What happens when a high noise factor, a low epsilon, is necessary, but the output becomes statistically unreliable for clinical decisions?
And that is the perpetual negotiation in DP. For research purposes, a low utility loss is often acceptable. But for high-stakes operational systems like real-time factory monitoring or air traffic control, where pinpoint precision is mandatory, the slightest level of noise can lead to disastrous consequences. In those environments, engineers might opt for zero noise and instead rely on rigorous access control and data minimization. They'd be sacrificing the provable privacy of DP for the guarantee of 100% data utility. The context of the application always dictates the acceptable compromise. #C. Privacy by design and performance. Federated Learning FL. Moving from protecting static data stores to protecting ongoing machine learning processes brings us to Federated Learning FL, which is often championed as the true privacy by design solution for training models on sensitive distributed data. The mechanism of FL inherently prioritizes privacy by distributing the computation to the edge clients. So instead of the client sending its sensitive raw data, like your daily health logs, to a central server, the central server sends a model framework. The client trains the model locally using its raw data, and then it only sends back aggregated updates, the gradients and weights, to the server. The highly sensitive raw data never leaves the device.
FL is a massive leap forward in privacy protection against that central server. But we know the trade-off here. Even those aggregated updates aren't perfectly secure. They can still leak sensitive information through sophisticated inference attacks.
That's the vulnerability. Researchers have shown that if the updates are aggregated from too few users, or if the model architecture is known, it's sometimes possible to reverse engineer the original raw data, or at least infer highly sensitive things about the people in the training set.
So this necessitates combining FL with DP to create a more robust hybrid solution. You mentioned two key ways to combine them: noisy learning and noisy data. The performance difference is staggering. Why is noisy learning so much worse?
So the first approach, noisy learning, applies Gaussian noise directly to the learned gradients before they are sent to the server. The sources show that while this achieved very strong privacy levels, an echelon of about 2.2, the performance cost was massive. The models trained in this scenario performed approximately 35 times poorer in accuracy than the non-private baseline model.
35 times, that's huge.
It's unusable. The reason is compounding. The noise is applied to the fundamental components of learning, the changes the model makes. If those changes are heavily perturbed before aggregation, the overall model convergence is just severely hampered. The server ends up aggregating noise, not clean learning signals.
That 35x performance hit is commercially unviable for almost any application. So the second approach, noisy data, must be the preferred compromise, right?
Absolutely. Noisy data involves adding Laplacian noise directly to the raw data on the client device before the local model training even begins. So the client trains the model on perturbed data, but the gradients it sends are derived from that perturbed data. While this still hurts performance, the noise is applied just once, at the input layer. This allows the rest of the learning process to be cleaner, which leads to much better model utility than poisoning the learning updates themselves.
But even with a noisy data approach, the model accuracy is still compromised by the noise you need for privacy. So how do we close that utility gap?
Optimization is the key to managing that compromise. One highly effective mechanism introduced in the research is clustering. Instead of trying to force one single global model onto a highly diverse user base, say health data from marathon runners and sedentary individuals, you group users based on similar behavior, meal logs, activity patterns, demographics. You then train personalized federated models for each group. And the benefits are twofold, tackling the performance and utility corner of that PPC triangle. First, clustering significantly reduces the computational burden and training time because the server is only aggregating updates from relevant smaller cohorts.
Right.
Second, and critically, when testing this on an augmented fit-bit dataset, clustering users who had their raw data noise for privacy resulted in an average reduction of 38% error in prediction accuracy compared to using a single global noisy baseline model. This confirms a crucial insight. Finding similar users helps the model learn more effectively, even when the source data has been intentionally perturbed for privacy. Smart distributed design can overcome the utility costs of privacy measures. #D. Infrastructure and computational trade-offs. Distributed storage and outsourcing. And let's briefly circle back to constraints governing raw infrastructure and computation, where those fundamental trade-offs between resilience, cost, and efficiency are still the primary concerns. In large data centers, the goal of distributed storage isn't just to store data, but to repair it affordably when a drive fails. This is where concepts like regenerating codes come in. They focus on the optimal trade-off between minimum storage regeneration, MSR, and minimum bandwidth regeneration, MBR. MSR focuses on minimizing the amount of storage space, we call that alpha, required at each node to hold the parity info you need for reconstruction. MBR focuses on minimizing the total network bandwidth delta that is required to transmit data across the network to repair a failed node.
I can see why this is a trade-off. If you store maximum redundancy, so a high alpha, you might need less bandwidth, a lower delta, to repair the node because the required data is just scattered everywhere. But that maximizes your storage cost. If you minimize storage, a low alpha, you must maximize bandwidth during a failure event to pull pieces of data from many different nodes.
Precisely. Data center operators have to manage this curve constantly. Network bandwidth is expensive, and it's often constrained during a failure event because the network is already under stress. By designing specialized codes, engineers ensure high reliability and cost efficiency by finding that optimal engineered point where the storage overhead is acceptable, but the bandwidth requirement for recovery remains low enough not to choke the network.
Okay, let's pivot to outsourcing complex computation. When a resource-constrained user needs to outsource a massive mathematical problem, like solving a system of linear equations, to a powerful cloud service, the trade-offs shift back to secrecy and efficiency. This leads to cost-aware secure outsourcing, CASO. The critical goals of CSO are maintaining secrecy, hiding the input, the problem, and the output from the potentially untrusted cloud, and ensuring efficiency. I mean, the computation complexity has to remain practical. The source is targeted feeder dollar complexity where TDOK problem size.
And that dollar complexity target is the defining constraint. The mechanism used is affine mapping. The user transforms their original problem variable, $6, using a secret transformation matrix, top dollars, and a vector to a new variable $. The cloud solves the transformed problem, and then the user applies the inverse mapping to recover the true solution. But here is the massive cost constraint. If that transformation matrix were a dense general matrix, the transformation in the inverse mapping would require matrix multiplication with a complexity of dollars operations.
So for a problem with a dimension of $1,000, 3 is $1 billion operations. 282 is only $1 million.
Exactly. If the complexity is 132, the resource-constrained user would spend an unacceptably long time just setting up and receiving the result. It would defeat the whole purpose of outsourcing to save time.
So to meet that efficiency goal, the transformation matrix dollar can't be general. It has to be carefully structured.
It has to be. The matrix dollars is specifically selected to be diagonal or a permutation, band, or sparse. This structure dramatically limits the required computational complexity for the matrix operations. It ensures the scheme is efficient enough for resource-constrained users to actually use, while still providing enough cryptographic protection to hide the true nature of the outsourced problem from the cloud provider. It's a perfect example of how computational complexity itself becomes a non-negotiable cost constraint in secure system design. #tag outro.
What a detailed exploration. We've traveled from the abstract constraints of consistency and availability all the way to the tactile constraints of memory utilization on a tiny Raspberry Pi, all governed by the same fundamental principle. So the core takeaway for you, the listener, is that in system design, perfection is not the goal. Chasing the high score in every single metric, whether it's privacy, performance, consistency, or cost, will ultimately lead to architectural paralysis or resource exhaustion. Success lies in making conscious, engineered trade-offs that align perfectly with the required tolerance for compromise defined by the application's specific needs. You have to know exactly where and why you are compromising.
We really did shift the discussion today. We moved from the binary constraints of CAP, where you sacrifice C or A, to the nuanced, multidimensional optimization required for privacy, performance, and cost. And the results are encouraging. We've proven that it is possible to maintain robust privacy with minimal impact on utility, but only through intelligent design choices, like the feature selection mechanism of DIGs or the complementary clustered use of differential privacy and federated learning.
And that brings us to our final provocative thought. We observed that maximizing privacy by forcing data generalization and strategic encoding resulted, counterintuitively, in a slight increase in the prediction accuracy of a machine learning model. This suggests that intentionally compromising one dimension by forcing data into a less sensitive format can sometimes simplify the problem domain for another dimension, actually increasing performance. So, what unexplored constraints in system design might yield similarly counterintuitive performance-enhancing compromises if we stop thinking about a simple balance between trade-offs and start seeking highly specific, engineered optimization?
Something to ponder as you approach your next big decision on which attribute is truly non-negotiable for your system.
Thank you for joining us for the deep dive. We'll see you next time.